Okay, hi everyone, welcome back. So another data analysis video. So in this video, I'm going to demonstrate how to run a simple linear regression model in Python using stats models and also using the Pingouin software library. So in the previous video, I covered diagnostics and tests of assumptions for regression. It was actually split over 6 videos. So what I'm going to do now is move on and actually fit some models. We'll start with the most simple ones like this, simple linear regression, and then move on to some more complex multiple regression models where we've got scale and in some cases categorical variables as independent variables. So in this case, simple linear regression, we use this when we want to assess the relationship between two scale variables. So where one is considered to be an independent variable and the other is a dependent variable. Okay, so we use the assumed linear or straight line relationship between our two variables to allow us to fit a regression model using what's known as the ordinary least squares method. And then we use scores on the independent variable, the IV, to predict scores on the dependent variable, the DV. So in a simple linear regression model, we may have a DV, we definitely, in a simple linear regression model, we have a DV and only one IV. So that allows us to plot the relationship between our variables using like a Cartesian axis plane, where we can plot the independent variable on the x-axis and the dependent variable on the y-axis and use a scatter plot. And regression models, they make use of the equation for a straight line, which you probably learned at school in algebra. That equation is in slope-intercept form. I believe it's y equals mx plus b. And in this equation, y is our score on the DV, m is the slope of the line, and it can be negative or positive. X is a score or value on the independent variable, and b is the intercept, or the point at which the regression line crosses the y-axis when we input a value of 0 for x, the IV. Okay, so y equals mx plus b is the equation for a straight line. You'll often see for the regression equation written slightly different to this. It's often written as y equals alpha plus beta x. So where alpha is the intercept, beta is the slope of the right line. So alpha replaces the b in the y equals mx plus b, and the beta represents the m for the slope. So y equals alpha plus beta x, and then sometimes you see it written with some plus epsilon, which would be some sort of small error term or something like that. Okay, so in this particular video, what I'll demonstrate is a couple of ways to run a simple linear regression model using Python. And specifically, I'll kind of obtain a regression plot for our data using the Seaborn library. So we'll create a scatter plot and fit a regression line to it using Seaborn, and then use the statsmodels software library to fit a regression model and obtain the parameters and statistics that are of interest to interpret the model, so we can understand what the relationship between our IV and DV is, if there is one. I'll also demonstrate how to run the same analysis using the Pingouin software library. Both methods are really similar to implementing, and they're quite straightforward, essentially. So the data that I'm going to use here for this analysis it's a data file used by Tabachnik and Fidel in their textbook using multivariate stats. So it's a really good textbook. I use it for postgraduate teaching, so for postgraduate research methods and stats courses. The data file is about women's health, and it was recorded from female residents of LA in 1976. So it's a reasonably big data file. I'm assuming it's a real data file that was collected back in the 70s. And the variables of interest for the regression analysis I'm going to run now are an IV called stress and DV called men-heal. So the stress IV is a scale variable measuring a participant's stress level from kind of low to high, I guess, on some scale. And this variable was calculated as a weighted measure of the number and importance of life-changing units over a year. So higher scores do indicate more stressful life events in someone's life. And the men-heal DV, which I believe stands for mental health, is a scale variable measuring the frequency count of the number of mental health problems experienced by a participant in that same year. Okay, so with this regression analysis, we're looking to see if stress, the IV, is a predictor of number of mental health problems experienced by the participants. So mental health is the DV in this case. Okay, so what I'm going to do is I'm going to import the software libraries that we need. I'm going to import pandas as PD, numpy as NP, matplotlib.pyplot as PLT, seaborn as SNS. I'm going to import statsmodels.api as SM, as statsmodels, and then I'm going to import statsmodels.formula.api as SMF, as statsmodels formula essentially, so this little nickname that I'm giving it. And then I'll import pingouin as PG as well. These are kind of standard nicknames used for these different software libraries. So if we run that, and I'll also import the data frame. I'm saving it as an object called DF, just an abbreviation for data frame. And I'm going to import it using the pandas read_CSV method. So you can see a number of variables here. Time at doctors, I think that's how many times to visit a doctor. Physical health, number of physical health issues. Mental health, number of mental health problems they've reported. Stress, some sort of scale. It's obviously quite a large scale. Scores between 86 here, 415. Religion and race, those are categorical variables. We're kind of not going to worry about those. The ones we're interested in just for this particular quite simple linear regression is stress, which is our IV, and mental health, menheal, which is our DV. Okay, so and we can see that they both appear to be integer values measured on some sort of scale. So first of all, what I'm going to do is use the seaborn regression plot method to visualize the data, and this will give us a regression line fitted so we can see what it looks like. So to do that, I'm going to call seaborn, so SNS, and then .regplot, and I'm passing in the following arguments. I'm specifying the data is our data frame, the x-axis variable is stress, and the y-axis variable is mental health. So then if we show that, what we can see here is this is our data points plotted. So there's a lot of data points. There's kind of quite a lot of participants in this data. They kind of seem to be like horizontally in quite straight rows, some of them, because I'm assuming that mental health can only take on certain integer values, and that's kind of accounting for that to some extent. And then stress on the x-axis. But you can see it's fitted a regression line, and these shaded areas represent sort of 95% confidence intervals for that line. They're much wider at this end because we've got fewer data points kind of to base our estimate on, essentially. So what the above regression plot is showing is kind of a weak linear trend between the stress independent variable and the mental health DV. Okay, so there's a large spread of mental health scores over scores on the stress variable below about 400. So if we look below 400, there's like there's a big spread of scores there. Most of the data points are stress scores of 400 or lower. There also appears to be a couple of participants with quite extreme stress scores. These ones here. Definitely, maybe some of these even, above 700, and they don't seem to have particularly high scores on mental health. These values two here are likely to be influencing the slope of the regression line and the overall fit of the model. And we may want to use various regression diagnostic tests for influence and outliers, and then consider removing those scores. But despite these values, I'm not going to do that here. I'm just going to kind of go along with interpreting the model as it is. But if we are really analysing this data, we want to think carefully about that. And despite these values and the spread of mental health scores at lower stress values, we can see that the regression line is indicating this kind of upward pattern in the data, where mental health scores increase as scores on the stress variable increase. We can also see, that shaded area around the regression line representing the 95% confidence intervals. Those are, as I said before, they're quite narrow in this area where we've got data points to base our estimates on, but more spread out up at this end of the X variable scale. And I guess this spread's also going to be, it's going to be influenced by the fewer data points, and the position of that is being influenced by those extreme scores and fewer data points to assess the slope as the stress scale increases in value. So given this plot, we would most likely want to check the data meets the assumptions of the regression model and perform some diagnostic tests before being confident in our interpretation of the regression model coefficients. But I covered those topics in like the previous 6 videos about diagnostics and assumption tests. So here I'm just going to fit this model and look at the output of the data as we see it plotted here. We're not going to remove any of these data points, we'll just go with it. Okay, so I'm going to fit a linear regression model to start with using stats models, and here I'm going to use I'm going to create this object called mod_1, so model 1, and that's going to be SMF, so I'm calling statsmodelformulas.ols, so I'm calling the ordinary least squares method from statsmodels formulas, and I'm passing in as a string the actual regression equation we're interested in. So mental health, RDV, is a function of stress, is what we're kind of specifying here. Specifying we want the DF data frame, and I'm doing it all in one line with the dot fit here at the end. And if I run this, if we call the summary of the results and run that, you can see we get this nice table of output. The top part gives us a number of gives us the model fit, the F statistics and probabilities, gives us a number of other things we can use to interpret how well the model fits, such as R squared and adjusted R squared. And then underneath we've got this coefficients table here, where it tells us the coefficients, so the slope of the line for stress, and whether it's a significant predictor in the model. And then we've got some other kind of diagnostic tests and stats down below that are quite useful. We're going to kind of ignore those for now though, and what we're seeing from this output is we can firstly assess whether the model is significant using the F value, so that model fit table, this top bit here. So we can use this F value and the probability of the F statistic, which is very small. So we've got an F value of 73.34 and a p-value of 1.63 times e to the negative 16. So it's a very, very small number. We'd have to move the decimal like 16 places to the left to actually get the exact p-value, but it's much less than 0.001. So we've got an F value of 73.34, an associated probability of P is less than 0.001. This indicates that fitting the model is better than just using the mean value of mental health when trying to predict mental health based on stress scores. So that slope of the line is better than using a line of 0 effectively, is what we're saying there. So in a simple linear regression model where we have only one IV, this tells us that the IV stress is a significant predictor of mental health scores. So next, if we look at the part of the table containing the coefficients, we can see that the coefficient for stress is 0.0114. So let's go back and have a look at that. So you can see here, this bit of table, stress, coefficient, 0.0114. That's the slope of the line, of the regression line, essentially. So it's not a very steep line, a very steep slope of the line, but the fact that it is a positive value tells us that as stress scores are increasing, so are mental health scores. And the t-value on that same line in the coefficients table, which is associated with the stress variable, also confirms what we knew from the significant F test, that stress is a significant predictor of mental health. So if we look here, we know we've got a significant model. It tells us our predictors are significant, or one of them is. We only have one in this case, and we see we've got a t-value of 8.56, p is less than 0.001. Okay, so if we were conducting a multiple regression and had more than one independent variable, then each independent variable in that coefficients table would have an associated t-value that would help us to interpret whether that variable was actually contributing significantly to our regression model and could be used to predict scores on the DV. When there's only one IV like this here, the t-value will be the square root of the f value for the model. So if we look at this t value here, if you actually square that 8.564, you will get a value that if you round it to 2 will be like 73.34. So the f statistic. Yeah. Okay, so so the last thing worth checking in the output in the kind of model fit part of the table is the r squared value, and that gives us some sort of indication of how well the model fits the data. It gives an idea of the variance explained. So in this case we have an r squared value of 0.137, so let's look at that if we go to the top. 0.137. So we've got this r squared value of 0.137, and that suggests that about 13.7% of the variability in mental health scores can be explained by scores on that stress variable. So there's obviously, so that's not a lot of the variability. There's obviously a lot of other factors, a lot of other variables that predict mental health scores beyond stress level. So that tells us that although we have a significant model and we can predict mental health scores using stress scores, there's a lot of noise in the data, and stress isn't a great predictor of mental health. And that fits with our interpretation of the original regression plot. We could see there was a lot of noise in the data, and mental health scores varied considerably at all levels of the stress scale. So if we go back to that regression plot, loads of, pretty much the whole scale of mental health scores here. Almost a square of data, really. Okay. All right, so that is kind of how to interpret the output. To form the report, though, the key statistics that we've talked about there, we could use the following formats. To report the f value, we'd report an f, open parentheses, and we'd put the between groups and the error degrees of freedom. That's a 1 and 463. Report the f value, 73.34, comma, p is less than 0.001. Same for the t value, t, open parentheses, put the degrees of freedom, 463 is equal to 8.56, p is less than 0.001. If we wanted to actually write out the regression, the equation from our model for the regression line, then that would be equal to, so men-HEAL, so mental health scores, is equal to 3.79, that's our intercept. So let's look to see where that is. Essentially, if we look at the coefficients table and the coefficients column, we have our slope for stress, and it gives us the value of the intercept on the coefficients. So 3.79, that's where that came from. Okay, so 3.79 plus 0.011, so I've rounded that to 3 decimal places, but then that is, as you can see, that's our slope of the line for stress times stress, whatever the score is on the stress variable. Okay, so that's the equivalent of y equals alpha plus beta x-ray. Yeah. All right, so to get this model output here, I kind of ran the model, fitted it, and then used .summary, mod1.summary, and it gave us this nice HTML printout of the results. If we take model1.summary and put that in parentheses as part of a print statement, it will give us the same output, but it will give us output that is formatted in the same way as you get if you run this kind of analysis in R. So it looks like that. This is exactly the same output as we got above, but in kind of an R style, in the style of the R programming language. Okay. All right, so that's stats models, simple linear regression. So I said I'd demonstrate the same thing using Pingouin as well. So we can perform the same regression using the Pingouin software library. So I'm going to create a new object called mod_2, model2, and that's equal to pg, penguin.linear_regression. Yeah, and then in parentheses, I've got to pass 2 objects to it. One of them is our IV and the second is our DV. So I'm just passing in the IV and the DV, the X and the Y variable. And then I'm going to ask for the model 2 out. I'm just going to call them the output of this model object, and .round and then parentheses 2 is just, I'm just telling it to round to 2 decimal places so the table looks neater. And what you can see here is you get a much simpler table of output. It doesn't give you the same information as we got with stats models. It gives us our coefficients table essentially, but it does give us R squared. So for the stress variable, you see we've got our t value and p. Because I rounded it to do so, just rounded it to 0.0. So it was less than 0.001. It gives us the slope of our line and our intercept, as we saw before. Doesn't give us the f value, but remember what I said, you can just calculate that yourself. So if you take the t value for the IV in a simple linear regression model, 8.56, and square that, it will give you the f value. Okay, and we know where we only have one independent variable in a simple linear regression model, we kind of, if we've got a significant model, we know that the predictor has to be, that one IV has to be significant. When we're conducting multiple regression where we've got like a number of IVs, Pingouin does have some other useful functionality in that it has methods that allow us to partition the R squared value, so we can see the relative importance of predictors in our model as well. So that's kind of something I will come on to in future videos anyway. So let me wrap this up. So that was just a simple linear regression model. So simple linear regression allows us to model the relationship between a scale IV and a scale dV using the equation for a straight line. The regression model can be used to assess whether the IV can be used to predict scores on the dV. When we have only one IV, it is useful to plot the variables using a scatter plot, and we can fit a regression line to visualize the relationship prior to fitting our model. Visualization will also highlight any potential issues with our data that we might wish to address before interpreting the results of the regression. I didn't do anything to, we kind of highlighted there may be some issues with this data set, but I didn't do any diagnostics to remove anything beyond just fitting the model. Okay. So regression models can be fitted using the statsmodels software library or the Pingouin software library, as I've shown in this particular video. Both are pretty good. Statsmodels gives you kind of some pretty good output as well. Okay, I hope that was useful, and thank you for watching and listening. And I think in the next video, I'm going to do another simple linear regression model, but I will do it manually. So I will actually use code to fit the model to obtain the coefficients and things manually without using one of the kind of software packages that has this type of method already contained within it. Okay, thank you. Bye.